Okay, so this is the 13th lecture. What we're going to talk about today is the concept of joint random variables. I guess just before I say that, I'll point out that due to the schedule disruption from the anomalous cold temperatures and spring break, the homework is now on a schedule which should be more favorable to you, whereby the homework that's assigned 1 week reflects the material from the previous weeks. So, homework 5, which is the one you're presumably intending to work on next, involves the material from the 2 lectures before spring break and not the material from this lecture and the subsequent one. The material from this lecture and the subsequent one will be on homework 6, which will be assigned this coming Monday. Okay, so as we have been discussing, random variables represent the result of measuring numerical quantities in any kind of context you want to interpret that. All you need is a number that you've generated somehow and you feel you're interested in. And what you want to do is measure this number over and over again and use the math we're studying in this course to come to interesting conclusions. So what we want to do now is introduce the idea of measuring multiple quantities in the same experiment. So this is done via a concept we call joint random variables. So, joint random variables, hopefully the name is suggestive. It's just, instead of measuring a single number, we're measuring several different numbers associated with this experiment, and we want to understand the statistics of how they're not only changing individually in time, but how they're related to each other and how the various changes over time may or may not be correlated and evidence of some kind of underlying phenomenon that is of interest to you. So, the basic hypothesis is that, you're a scientist and you have 2 different properties of your experiment. Let's say we have a light bulb and we can measure its color and its intensity, and so we might be interested in varying or measuring the color and intensity over time and seeing whether it's changing. And so if we just were measuring intensity alone, this would be a single random variable. At different points in time, we would have different numbers which represent the intensity of the light bulb, and we can do expectation and variance and with those numbers like we've been used to. So, what's different about the situation I'm describing now is that rather than just considering intensity as a single random variable and considering color as a single random variable that has its own properties, we're going to think of them as 2 coordinated numbers that not only have individual trends over time, but we want to discover the extent to which there may be trends in a relationship between the two quantities that we're measuring. So, what the idea we want to use in order to formalize this kind of empirical situation is to use the same strategy mathematicians always do, which is to build new concepts by generalizing ones we're already comfortable with. And so, as with single random variables, there are three equivalent formulations of joint random variables, which we'll define on the next page. And the basic idea is just to make multiple copies of the objects that define single random variables. So we'll first discuss discrete random variables, because that's what you should always do. And we had measurement functions, probability mass functions, and cumulative distribution functions, which were three equivalent definitions of discrete random variables. And so we want to get three different versions for joint random variables as well. Okay, so we can have a look at all this information, and let's read the top row first. So the top row of definitions describes how to think about two random variables which are being measured at the same time. So we have two measurement functions, x and y, and every outcome in our sample space has two measurements associated with it, which we'll write as x of omega and y of omega, where omega is the outcome. So this is, again, the most concrete way to understand joint random variables, and it's the theoretical basis for everything we do with joint random variables, because it connects them to sample spaces and thereby to the axioms of probability. But I'll tell you exactly the same story I told you about single random variables, which is that directly working with measurement functions almost always presents you with an overwhelming amount of data, and the main task of mathematical probability and its applications in statistics is to do something more useful than just collection gigantic quantities of measurements. And so measurement functions are the theoretical basis of everything we do. Mathematically, they're how we connect it to the axioms, and in real world terms, measurement functions are the actual data that you're working with to start whatever kind of statistical analysis project you're endeavoring. And so you can think about the situation I described before with color and intensity of a light source. So in that context, omega would just be timestamps. So you could have omega be like 0 seconds, 1 second, 2 seconds, and we would have color at 1 second and intensity at 1 second, color at 2 seconds, intensity at 2 seconds, and we would just keep measuring things every second. Every second we would have a pair of numbers, which are the two measurements associated with this outcome of the random variable at time corresponding to that second. And so in interpreting it scientifically, the outcome is the underlying physical state of the light bulb in the most general sense. So, what we're measuring is a physical system called a light bulb, which has all kinds of protons and electrons and quarks and fields and magnetic properties and all of this possible information you can measure about this physical system called a light bulb. And the outcome at a certain is the physical state of the light bulb at a certain time, which we think of as varying according to some random law. And then when we're doing with these measurement functions is to observe certain properties of omega, whereby we look at specific numbers that we can determine based on the overall physical state of the light bulb. So if omega is the physical state of the light bulb after 1 second, we can say, associated with that, I have a number called color and a number called intensity. And so those are just two numbers. They don't describe every single possible detail of the sample space, but when you're doing a scientific experiment, you kind of hypothesize the sample space as the ultimate physical state of the system, and then you think of your random variables as giving you numbers that have information about these outcomes omega, which represent the physical state of the system at different times. Okay, and so the first step we want to take into mathematical analysis of double measurement functions is what we're going to call a double probability mass function. So a double probability mass function is a grid of numbers in the unit interval with sides indexed by values of x and the other side indexed by values of y. So if you recall, the probability mass function for a single random variable, we were able to encode as a table. So we want to think of as a linear table as a one-dimensional grid where you just have labels and cells with a one-to-one association between labels and cells with outputs. So we had probability mass functions for single random variables described as tables where there's a one-to-one correspondence between the labels in the top row given by values of the random variable and the probabilities of achieving those values in the bottom row. But now for a double probability mass function, what we're going to have is a grid of numbers with sides indexed by values of the first random variable along the rows and values of the second random variable along the columns. And then in each cell, we're going to say, all right, because I've labeled my sides by values of x and values of y, I can think of my cell as giving me a pair of values. So each cell is indexed by a pair of values. And what you do in this grid is you fill in the cells based on the probability that the two random variables achieve those two values simultaneously. So the grid for the double probability mass function is indexed by values of the two random variables separately along the rows and columns. And in each cell, you put the probability that the random variables simultaneously take the two values indicated by the two labels of that cell. And then we have also a concept of a double cumulative distribution function. So just like with single random variables, cumulative distribution functions are ultimately the most mathematically fruitful way to express a random variable because they are functions defined on an entire Euclidean space and taking values in another subset of the real numbers. And like I was saying with probability mass functions for single random variables, the issue with probability mass functions is that you can only get useful answers when you input something you already know is a value of the pair of random variables. And most real number inputs to a probability mass function will just give you an answer of 0 because if the random variable is discrete, there's only a finite number of possible values, and so you're just going to get 0 as the probability for any real number which is outside of the finite list that's actually taken. And so it's the same story with double probability mass functions. You have a finite list of values of x and a finite list of values of y. And so if you take pairs where the first thing is in a finite set and the second thing is in a finite set, the number of pairs is still finite. So there's only a finite number of pairs where the probability mass function actually gives you useful information and tells you a positive probability of the random variables achieving that value pair simultaneously. Whereas with the double cumulative distribution function, you get useful information for pretty much any input that's not way too far down or way too far up. And so what you ask for the double cumulative distribution function is you think about it as a function that's defined on a plane. And so it takes a pair of real numbers as input and returns the probability that the first real number or the first random variable is less than or equal to the first real number, and the second random variable is less than or equal to the second number. So it puts an upper bound on the first random variable, an upper bound on the second random variable, and asks for the probability that the pair simultaneously satisfies that coupling of upper bounds. Okay, so we can generalize this idea even further to arbitrary finite lists of measurement functions, where now we want to think we're measuring n different quantities associated with our system. So let's say we have this light. Instead of just looking at a light bulb, we're looking up at the night sky, and we can measure all kinds of crazy patterns coming in from different aspects of the large-scale universe. And so we have all really long list of possible things we want to measure when looking at the night sky. It's like there is no end to the number of things you can try and measure with a telescope that simply absorbs incoming radiation from space. And so maybe we have like a billion different things we're trying to measure about what you see when you look up at the sky. And we have a billion different things we're trying to measure with some super powerful model of general relativity that we're using to get novel insights into the structure of reality. And so we have all this randomness, which is being measured in all these ways, and we're still thinking of the sample space as all the physical states of the universe that we could possibly have as we go through time. And we're measuring a list of parameters associated with the physical state of the universe. universe. And those parameters are numbers that are giving us information about the underlying state of the system, which is encoded as outcomes in the sample space. So, in order to interpret or to analyze multiple random variables mathematically, we make the same generalization from lower dimensions to higher dimensions that we made in going from single random variables to double random variables. So we had a linear table to record the probability mass function of a single random variable. And we have a grid of numbers to record the probability mass function of a double random variable. And so if we have a list of n random variables, we're going to have an n-dimensional hypergrid with sides indexed by values of each parameter we're measuring. So if you have 3 random variables, your probability mass function will be naturally arranged in a cube. And if you have a billion random variables, your probability mass function will be naturally arranged in a billion-dimensional hypercube. And if you're familiar at all with the cutting edge of machine learning, it's precisely analyzing these extremely high-dimensional data structures, which are commonly referred to as tensors. So what I'm calling an n-dimensional hypergrid is mathematically known as a tensor. And, Google has this system called TensorFlow, which is based on a completely novel architecture for a computer chip that has that's sort of a third generation thing. Originally, computer chips had what are called central processing units, CPUs, and then people started developing what are called graphics processing units, or GPUs. And then there's been a third generation just since 2016 where Google's developed these so-called tensor processing units, which are specifically designed to work with these high-dimensional hypergrids of numbers that come up in large-scale data analysis where you have huge numbers of parameters you're measuring about a physical system. And so if you're actually working with something that's more than three-dimensional, you're not going to be able to visualize it yourself, and you're going to have to trust your understanding of theoretical math together with your skills in coding Python or whatever other language you're using to actually work with these objects, because you're going to have to understand theoretically how four-dimensional tensors work, and then you're going to have to be able to interpret it in terms of something you can code into a computer so it can do four-dimensional computations for you. But all we're going to do with multiple probability mass functions in this course is going to be in 2 or 3 dimensions, and all of the computations will involve something like at most 10 data points. So I'll make sure that everything is small enough in the actual assignments in this course that you don't have to worry about the problems that are central to modern big data science, where you have high dimensional grids with huge lists of numbers. I'll make sure I keep it in 2 and 3 dimensions, which are friendly to the human eye, and small lists of numbers which are friendly to the human brain. So we also have a concept of a multiple cumulative distribution function, which is defined on a high-dimensional Euclidean space. So the dimension of the domain of the function is the number of random variables you're measuring in your ensemble. So you have a list of random variables, and what you're doing is you're thinking of this function defined on Euclidean space of dimension n. So it's a function which takes an n vector as an input. You give it this list of numbers t1 up to tn. And what the function tells you is the probability of your ensemble of random variables simultaneously satisfying all of these upper bounds. So you input t1, t2, up to tn into the multiple cumulative distribution function, and what it tells you is the probability that your first random variable is less than or equal to t1, your second random variable is less than or equal to t2, your third random variable is less than or equal to t3, so on like that. Okay, so let's see this example where we let x be the sum of two fair dice, and we let y be the absolute value of the difference. So what we want to do is to find the joint probability mass function and cumulative distribution function of x and y. So because this is the first example we're doing with joint random variables, I'm going to use the method that always and forever works, which is just to write down the measurement function explicitly and count. So I'm going to write down the measurement function for x, which is the sum of two fair dice. So I have that table on the lower left, and I have, I guess it doesn't matter why these are first or second. I have this table on the lower right, which is giving me the absolute value of the difference between the two rolls. If I didn't have the absolute value, I would have needed to specify first and second because the table would not be symmetrical. But because I said absolute value, the table is symmetrical, and so I don't need to specify which one is the first die and which one is the second being subtracted. So the outcomes are all the possible states of a pair of dice. So we have the labels for the different states of the system. So these are not the labels that we use in our grid for the probability mass function. There's a unfortunate visual coincidence which is easy to lead your mind astray, and the labels, we're going to have grids on this page and grids on the next page, and despite the fact that we have grids in both situations, this grid is has labels that are telling us outcomes, and the next grid will have labels that are telling us values. But hopefully you can see that what I've done on this page is just kind of brute force writing out the two random variables for all the possible arrangements of two dice. Okay, so now let's think. What's the joint probability mass function of x and y? So the joint probability mass function of x and y is an 11 by 6 grid. So why is this joint probability mass function an 11.6 grid? 11 times 6 grid. Well, it has rows labeled by all the possible values of x. So I've written the measurement table for x on the lower left of this page as well, and we can see that the possible values achieved by x in this measurement table are all the integers between 2 and 12. So we're going to label the rows of our table with integers between 2 and 12 because those are the possible values of x. Well, I'm not actually going to draw the table, as you can see, because it would have 66 cells, and I just don't see the point of throwing 66 data points at a human being. And so rather than drawing it, also, I'm lazy and I don't want to write 66 data points myself, regardless of whether it would be comprehensible. So the point is, I'm telling you on this page how you would calculate any individual cell in this 11 by 6 grid. And what you do is you label the rows by the possible values of x. So in this case, we have rows labeled 2 through 12. And then what we need to do with the columns is label them by possible values of y. So you can see I have the measurement table for y written on the bottom right, and I have possible values 0 through 5. So in my joint probability mass function, I would have an 11.6 times 6 grid. The rows would be labeled 2 through 12, and the columns would be labeled 0 through 5. And so what we do in order to calculate the entry in a given cell, so to calculate the entry in row n and column k, what I need to do is I need to see how many cells contain n in the x measurement table, and then I need to see how many cells contain m in the y measurement table. So I have this 11 by 6 grid where the cells are labeled by a value of x and a value of y. And what I put in the cell is I put the probability that x is equal to the row number and y is equal to the column number. So let's see an example of how I can go about doing that. So I have my two measurement function tables where the left one is for x and the right one is for y. So I need to pick a pair of values where the left coordinate is a possible value of x and the right coordinate is a possible value of y. So I've just arbitrarily chosen 6 and 2 because 6 is an example of a number between 2 and 12 and 2 is an example of a number between 0 and 5. So 6, 2 is an example of a possible value pair which could be simultaneously taken by my two random variables. And in order to figure out what I would put in the 6, 2 cell of my table, I look at my measurement data and I see what proportion of the outcomes are simultaneously 6 on the left and 2 on the right. So I can see if I have the sum of, so if the first die is 4 and the second die is 2, the sum is 6. And if the first die is 4 and the second die is 2, the absolute value of the difference is 2. So that outcome gives me the value I'm interested in, where x is 6 and y is 2. I can also see that if the second die is 4 and the first die is 2, or if the first die is 4 and the second die is 2, then I also get a sum of 6 and an absolute value of difference 2. So the outcome where the first die is 4 and the second die is 2 gives us my desired pair for random variable values. And the outcome where the first die is 4 and the second die is 2 also gives me my desired pair of random variable values. So I include both of those outcomes in the event I'm trying to calculate the probability of. And I find that this event has 2 outcomes out of a possible 36. And so I say the event that x is 6 and y is 2 has probability 1/18 because it involves 2 outcomes out of 36 possible outcomes. And I could do the same calculation with any pair of inputs for pxy, where the first one is between 2 and 12 and the second one is between 0 and 5. Okay, so let's think about what the joint cumulative distribution function would look like. I haven't drawn it explicitly in mathematical rigor because it's kind of hard to draw. But I hope you can get some sort of intuition from what picture I have here. So the joint cumulative distribution function looks like a higher dimensional analog of a step function. It's like some sort of, when you have a normal step function, it looks like playing Super Mario in 1985. And when you have this kind of higher dimensional step function, it looks like playing Super Mario Galaxy in whenever it came out, I don't know, like 2010 or something. I like that game. But yeah, anyways, the point is you have steps that are now squares instead of line segments, and they're going up in 2 different dimensions, jumping every time you pass over a new value of the random variable. And what the square is it's the probability that... So let's have a look at the black square on the bottom left. So if I see the picture correctly, there are 16 black squares. And we want to look at the one that's on the bottom left, closest to the origin point of the 3 axes. And so what's going on with that square on the bottom left is that it represents the probability that x is between 2 and 3, and y is between -5 and -4. So the only outcome where that occurs, if we look, so where are the outcomes where x is, or sorry, I shouldn't have minus signs here. Let me get rid of that. But anyways, if I look at this square at the very bottom left, it represents the probability that x is between 2 and 3, and what the absolute value of the difference is between 5 and 4. So if I go back and I look here, I say, okay, there's 2 cells where the absolute value of the difference is 5, less than or equal to 5 and greater than 4. And then if I look at those two cells, I can also try and see the probability that x is greater than or equal to 2 and less than 3. And so there's no cells which satisfy both of those bounds. So that square is supposed to be represented at 0 because there's no outcomes where the absolute value of the difference is 5, and there's no outcomes where the absolute value of the difference is between 5 and 4, but the sum is between 2 and 3. So that square is supposed to be positioned at 0, and then the other squares jump around to different heights, which are multiples of 1 over 36, based on whether or not you can find outcomes which simultaneously satisfy both of those upper bounds. Okay, so let's have a look at an example which involves more than 2 random variables. So in this case, we have 3 random variables, and instead of looking at grids, we're going to be looking at cuboids. So a linear table is a 1-dimensional tensor, and a grid is a 2-dimensional tensor, and a cuboid of numbers is a 3-dimensional tensor. So what we have here is want to consider the temperature, color, and intensity of a light source in appropriate units every seconds for 4 minutes. And so we assume we make the following measurements. So in this case, I'm not even asking you to calculate a measurement function. I'm just telling you what the measurement function is. And that's pretty much what actually happens in the real world, you know? It's not the purpose of probability or statistics or data science to question how you get measurement functions. The purpose of probability and statistics and data science is to figure out what to do with measurements once you've already got them stored in some kind of electronic format. And so you have this kind of simple experiment where the temperature was 4 when it started, and the color was 11, and the intensity was 45. And then after 1 second, the temperature stayed the same, the color went up by 1, and the intensity went up by 2 to 47. And so we just have these various measurements that we recorded at different timestamps. Okay, and so what we want to do is to calculate the joint probability density function and the cumulative distribution function of these random variables. So let's say x1 is temperature, x2 is color, and x3 is intensity. And so the joint probability mass function is 2 times 2 times 3 cuboid, because x1 takes 2 possible values, 4 and 5. And the color takes 2 possible values, 11 and 12. And the intensity takes 3 possible values, 45, 46, and 47. So in realistic data analysis, what you often end up doing is just assuming that all the values are different and making the tensor for your probability mass function have length equal to the total number of timestamps. So if you look at what we have here, we can do it as a 2 by 2 by 3 cube, because temperature takes 2 values, color takes 2 values, and intensity takes 3 values. But another thing we could do that would be actually better for computational purposes is to avoid forcing ourselves to calculate the number of values in advance and just pad everything with zeros to give us a 4 by 4 by 4 cube. So if instead of checking the number of values and shrinking our tensor cuboid to have dimensions equal to the number of values, we could just have a 4 by 4 by 4 cube and pad zeros in the entries which have no information because they didn't appear as values of the function. But anyways, I've drawn it here as a 2 by 2 by 3 cuboid with labels for the possible values of color, temperature, and intensity. So I have 12 cells here because 2 times 2 times 3 is 12. And I've been able to label 10 of them. There's 2 cells which are hidden in the back. And I haven't been able to indicate the labels for those 2 cells. They're both 0. So if you assume the 2 cells hidden in the back are both labeled 0, you get 12 labels for the 12 cells in these cuboids. So let's see, how did I calculate these labels? So let's have a look at the one with a half, which is in x1 equals 4, x2 equals 12, x3 equals 47. So we look at x1 equals 4, x2 equals 12, and x3 equals 47. And why did I put a half in that cell? Well, if temperature is 4, color is 12, and intensity is 47, I can see that matches 2 different timestamps. I can see I achieved temperature 4, color at 12, and intensity 47 at 1 second and at 3 seconds. So from that, I can conclude that out of my 4 timestamps, half of them involved temperature, color, and intensity, satisfying 4, 12, 47 as the 3 values. And so I put a half in the cell 4, 12, 47 because half of the timestamps have x1 equal to 4, x2 equal to 12, and x3 equal to 47. And so we can see, why did I put a 0 in, let's say, the x1 equals 5, x2 equals 11, x3 equals 45. So that's the cell on the bottom left that appears to be closest to us and at the bottom. So it has a 0 in it. So why does that cell have a 0 in it? Well, if I look at what I'm trying to match, so I'm trying to match 5, 11, 45. And there are no matches in my table for 5, 11, 45. So that's why I put the 0 there. Okay, so hopefully you have a sense of how a computer that wasn't restricted by the structure of the human eye could manipulate even higher dimensional tensors involving more than 3 random variables. Okay. And so what's the cumulative distribution function of these 3 random variables look like? Well, if you remember, our cumulative distribution function for 2 random variables looked like Super Mario Galaxy with all these little steps you can jump around on that look like you're moving through a 3-dimensional space. And so if we boost the dimension of that, we again run into the limits of the human eye. And what we would want to see is a function defined on 3-dimensional space, which would have a 4-dimensional graph. And It would be a step function where the steps are shaped like cubes instead of squares, and they walk up the fourth dimension instead of increasing into height. But again, visualizing these kinds of things is a matter for people who want to study geometry as a theoretical mathematician. There's endlessly beautiful ways of connecting the human eye with higher dimensions, but for the purposes of data analysis, at least unless you're doing fundamental physics, what you want is just to say, okay, I know that these things can be visualized as cuboids in higher dimensions or step functions in higher dimensions, but I need to chill out with trying to see them and just accept that they exist abstractly, and I can do calculations with them using the procedures that I can visualize in lower dimensions. So if you have a list of more than three random, if you have something that's in a dimension too big to visualize, what you do is you pretend you just have two random variables, figure out what you would do if you just had two, and then trust that your computer knows what it's doing if you correctly make the generalization from what you understand in two dimensions or three dimensions to the dimension appropriate to your large number of random variables.